Hello, welcome to the GeoTeric training videos. This video will cover frequency decomposition, part of GeoTeric's Reveal module. GeoTeric's cognitive interpretation workflow has 4 stages: condition, reveal, interpret, and classify. Condition enables you to apply post-stack data conditioning to achieve the optimal seismic signal for your interpretation. Reveal allows you to see the geology that is hidden in the data using many techniques, including frequency decomposition and RGB blending. Interpret enables you to interpret the geology, whether it's faults, geobodies, or horizon surfaces, including interpreting directly on the RGB blends. And classify enables you to create facies classifications and to further investigate the geophysics behind the features that you see using the RGB blends as well as any additional volumes. So GeoTeric has 2 methods of frequency decomposition, a standard and high definition. This video covers the standard technique, but please see our HDFD video for training on the high definition approach. The frequency decomposition workflow is launched from the Reveal tab, and this opens the workflow window. The process is interactive and is run over a specified time slice or horizon of interest, but the result is fully volumetric. So this initial slice is just for the interactive parameter testing. So I select my data condition volume as the input and select the slice of interest. Then I press set down at the bottom. We now see the parameter window. So the first step here is to generate the frequency spectrum. This is run on a 64 sample window around the slice we've specified, and it shows us the frequency content of the target interval. Now these colored curves show us decomposition filters that will be applied to the data. We can alter these on the left-hand side, and you can see that we have 2 different types of filter available, the constant bandwidth and the constant Q. The constant bandwidth filter is a Fourier transform, so every central frequency has the same bandwidth and therefore the same filter length. This gives very good frequency resolution, as only a small sample of the frequency spectrum is extracted by each filter. But it gives very poor vertical resolution because long filter lengths are required, which makes the results look smeared vertically. The second option is the constant Q. Here we have a constant relationship between the center frequency and the bandwidth. So as the frequency increases, so does the bandwidth. This means that the filter length decreases as the frequency increases, resulting in much better vertical resolution. This is the same process as a continuous wavelet transform. The third option that we have is still a constant Q filter, but the central frequencies are distributed exponentially so that each band has a similar overlap point with its neighboring band. This distribution is useful when you have predominantly low frequency data or depth data. We can also adjust the minimum and maximum frequencies. Generally, you should ensure that the full frequency spectrum is covered so that you can look across or look at the data within the full frequency spectrum. You should also make sure you have a good level of overlap between the different bands. When the parameters have been set, you press the process button and GeoTeric will run the selected filters over the target interval. We then get 2 forms of preview of the results. The normal preview shows us the individual responses, the bandpass, the magnitude, and the phase results for each frequency band. We also get some spectral statistics volumes. These are really useful for some of GeoTeric's more advanced workflows, which you can see in later videos. Any of these can be processed as 3D volumes simply by ticking the box and giving the volumes a prefix name at the bottom. The different magnitude volumes show how different parts of a feature are showing up in different frequency bands, depending on their relative thickness and rock properties. But it is much more effective if we can see all that information simultaneously. And we can do that by going back and selecting the Colour Blend preview. Now we can blend 3 magnitude volumes together using a red, green, blue colour blending system. And this shows us the relationship between the different frequency responses. Where we have a strong response from all 3 frequencies, we will get an area of white. Where we have a low response from all 3, we will get black. And where one frequency dominates, that colour will be strongest, like in this zone here, for example. To look at different frequency combinations, we simply change the input volumes. When we have frequencies that are spaced apart, we get more colours in the display as there's less overlap between them. When we choose frequencies that are close together, the response is less colourful as there's more overlap between the frequency volumes. This is particularly noticeable with the constant Q, as that already has a higher level of overlap between the different bands. The technique used, and therefore the bandwidth of the individual volumes, has a significant impact on the results obtained. And this comes back to the frequency versus time resolution I talked about earlier. So if we take some snapshots of the results and the parameters used, we can compare them and start to build a report. So starting with the constant Q results and repeating it for the constant bandwidth results, we can now see that the 2 blends with exactly the same central frequencies look very different. And this is all down to the bandwidth and the filter length. We'll look and compare the vertical sections in a couple of minutes when we go back into the 3D project. In GeoTeric, when we create the blends, it applies a max stretch by default. This simply normalizes the 3 volumes based on their maximum amplitude on this slice. If you have a data set like this one where we have a white spectrum, there'll be very little difference between the max stretch and the uniform stretch, where the same scaling is applied to all the frequency bands. However, if our spectrum had more of a gradual slope, or if we included frequencies at the edge of the blend, then the difference between using a max stretch or a uniform stretch would be much greater. There's also an option to apply a contrast enhancement. This applies a non-linear scaling to the individual volumes, and this allows us to enhance the low amplitude areas, to reduce the contrast between the high amplitude and the low amplitude. This can be really effective if your target is a low amplitude zone and it's hard to see it in a conventional blend. Applying a contrast value enables you to see these variations in colour and therefore frequency in the low amplitude zones much more effectively. Once we have a blend that we're happy with, we simply give it a prefix name and press Run. And GeoTeric will then apply those decomposition and blending of parameters to the full data set, and the results will appear in the main project tree. So now we can view either the individual input volumes or the blends in 3D and work with them in probes, in slices, on arbitrary lines, or draped on horizons. We saw earlier that the 2 different techniques gave very different looking results with the same central frequencies. If we look now at a vertical section through each of those blends, we can see the improvement in vertical resolution that is achieved with the constant Q method when compared with the constant bandwidth version, which gives us much more colour due to the better frequency resolution. So the best technique to use depends on the interpretation objective. Constant Q if you're looking for more accurate positioning, or constant bandwidth if you're looking for more subtle frequency differences in isolated layers. Once you have the blends in 3D, you can then go on to interpret what you see directly on the blends, whether it's horizons, faults, geobodies, or simple polygons. The RGB blends can also be used directly for facies classification using the classify module. All these workflows are covered in other training videos, so please check out our YouTube channel for further information. So remember, you should use the right technique for your interpretation objectives. Constant bandwidth is good for estimation of bed thickness and thin bed interference due to the high frequency resolution. Constant Q is good for regional studies and reconnaissance due to the good compromise between vertical resolution and frequency resolution. And GeoTeric's third technique, high definition frequency decomposition, is best for reservoir scale analysis and understanding depositional layers due to the very high vertical resolution. So there's more information about the high definition tool in the HDFD training video. Support for any aspect of GeoTeric is always available by emailing our global support team using support@geoteric.com. Please also check out our blog for more workflow suggestions and tips for other training videos that are available. Thank you very much indeed for watching this training video.